Okay, let's discuss few more concept about ICOFOAM that we started discussion in the last session. Okay, so let's look at what we gone through in the last session. So we started discussion about the ICOFOAM, and we look at the cavity for with a non-uniform mesh, and I ask you to please repeat the calculation for different REs. Okay, as well as I also ask you to look at the cavity with a skew angle 30, 45 and 60. Okay, and with different RE as well. And then I also ask you to please try to map a data between simple form and ICOFOAM for, let's say, very fine mesh. Try to refine the mesh. Okay, and check for, let's say, R equal to 400 for ICOFOAM result as well as the simple form result. So we able to finish up to this. Now let's explore exact transient nature of this ICOFOAM, because whatever we look at in the last session, even though our solver is unsteady, but we look at the steady state physics out of the unsteady nature of the solver. So let's explore today the flow over a circular cylinder, and for that we have to use this 2D circular cylinder one folder. Okay, so that is the first test case. So let's explore what we have here. So first, very quickly, we first create a mesh and I brief you about entire test case. Okay, so let's first create the mesh out of this, and for that we try to use this step-by-step process. Okay, so here is all the commands. Okay, so we're going to run for R equal to 250, so we have to make sure that exactly the same RE for which we are hoping we are running the case. Okay, no command because we didn't source the OF. Now let's first create the mesh file out of block mesh utility. Let's quickly check how the mesh is look like. Okay, so let me explain you the first test case. So this is a circular cylinder of diameter of 1 meter. Okay, and from this left side the incoming flow is approaching the obstacle, and this right hand side is the outflow. Okay, and top and bottom is the symmetric plane, and till we are working with the two-dimensional aspect of the flow only. So if you see, we have a 1 cell thick height, and let's explore how the mesh is look like. So previously we have a regular Cartesian mesh, but now this is called O-grid type of the mesh, and if we want to develop this mesh, we have to create certain blocks. Okay, so I will quickly walk through the block mesh file of this particular tutorial, and so it gives you the idea how you can create this circular pattern with the help of the block mesh. Okay, so before we go towards that part, let's explore how the blocks is look like in this para form. Okay, so total, if you see, we have a total 12 blocks. It's starting from 0. Okay, so let's first look at the blocks, how it look like. Okay, so let me zoom in this part. So what we did to capture this circular pattern, okay, we constructed the 4 blocks. Okay, 1, 2, 3 and 4. Okay, and let's switch off all the blocks and switch on only one. So this is the first block. Okay, then second, third and fourth. Okay, so with the help of this 4 block, we are able to capture entire this circular geometry very nicely. Okay, and this concept is called O-grid concept. Okay, so if you are aware, in the structure or body fitted mesh generation, there is a O-grid, C-grid, body fitted mesh and all this concept. Okay, so in that regard, it is called the O-grid concept of mesh generation. So let's switch on only one block. Okay, so if you see this block, okay, so number of points required is till 4, and how we created the points 0, 1, 3, 4. Okay, and correspondingly we have a 20, 21, 22 and 23. Okay, so that is how our block is look like. Okay, in the similar line, we have a number of few more blocks. Then if you activate this block, you can see from here 4, 5, 6, then we have a 7, then 8, okay, then 9, okay, and 10, and last one is the number is 11. Okay, so like that way we have a total 12 blocks available. So let's quickly look at how the block mesh dict file is look like. Okay, so if you see here we have a number of coordinates system. Okay, so I started with -10. Okay, let me brief you in the x direction how many points structure we have. We have a -10, -2. Okay, then exactly where we have a this midpoint, not exactly the midpoint of, but this point coordinate we required. Okay, so we have a this point coordinate system. Okay, with the help of block mesh. So that is 0.3535 like this way. Okay, so we have a -10, -2 in x direction, then -0.3535 this point, +5 the same way. We have a 2 that cover this point coordinate, and then we have a outlet at a location of 30. Okay, so and our center is exactly at the center point of this particular circular cylinder. So like that way we constructed the block mesh. In the same line, the y direction, we have -8. -8 is this location. Okay, then we have a -2. Okay, at this location, then we have plus minus 0.353534 this one, +3 this, and then 2 and 8. So if you have all these coordinates, with the help of that you have to first construct the blocks, and for that we require the all the points vertices. So slowly take your time and go through this all the vertices. Okay, so 0 mark is where 0 mark is here. Okay, 0 mark vertices is here. Okay, let me put it in the outline way. Okay, so if you see the outline way, this is the 0 coordinate. Okay, so from where we started putting the points 0, 1, 2, 3. Okay, or let me just show you only one block, so it will be easy. Okay, so switch off all the blocks, let activate only one block. Okay, apply. So look, if you see here you see all the coordinates. So 0, 1, 2, and here we have a 3. Okay, then opposite we have a 20, 21, 22 and 23. Okay, so to fix that coordinate we required certain values. Okay, so we in x direction we move with the 4th point, so x4. In y direction we move with the 3rd, so y3, and in z, z1, because we required only 2 points in the z direction. So this is back side, and backside all the points. That means I started giving the numbering backside, that means where our z is minimum. Okay, in that plane we can say it is a backside. So let me start. So this bottom plane is called the backside, and the top plane is called the front side. Okay, so like that way you can understand what is backside and front side. For in each one side we have a total 20 points, and 20 point in backside and 20 point in front side. Okay, with the help of that we are able to construct all the points. Now after that we have to construct the blocks. Okay, so block number 1, let me open that block. Okay, so this is block number 1. Okay, and block number 1 is constructed with the 0, 1, 2, 3, 20, 21, 22 and 23. Okay, so like that way we able to construct the entire block. So again we have to put, wait a minute, so I have to keep the coordinate system at, let's say, the way we are looking from the outside. Okay, so we say something like this way. Okay, so we keep the coordinate system at, let's say, at a 0 point. Okay, so 0, 1, 2, 3, that is the way to go. Okay, so ultimately if I fit the coordinate here system at a 0 location, so I can start numbering in the clockwise direction. But as I told you, you can start numbering from any of the location, but it make sure it's rotate in the clockwise direction. You can give the numbering between 0, 1, 2, 3, but here because we want to map the mesh, for that purpose I start numbering 2, 3. When you say 2, 3, so 2, 3 become is x-axis. Okay, So I kept, in place of 0, I kept the coordinate system at 2 location, but the scenario is exactly same. When you put the coordinate system at the 2 location and you are looking, so coordinate system is towards observer, and when the observer looking through the depth of the z, it's supposed to follow the right hand side or clockwise rotation. So 2 3 0 1, and from 2 connecting is 22 23 20 and 21. So in the similar line you can follow all the blocks and you will see the entire nomenclature. Okay, so please look at that entire block very carefully and try to understand how entire block mesh is constructed with the help of this total number of the blocks. Okay, so total we have a total 12 blocks. Okay, now along with that, here is this number of meshing size. In the previous case we fixed 30 20 like this way, but because we have multiple blocks and if we want to refine the mesh, it is very handy if we give in some type of number of cells with some micro. So here along with this all the points coordinate, I also defined few more variable. It is x direction cell size, y direction cell size and z direction cell size, and very quickly you can modify this size and you can create a very fine mesh. So here is the mapping. If you changing the x4, whatever the value you keep, same value is supposed to go with the y in the y direction cell 2. Okay, so if you violate this, then the mesh will not be created. Okay, so that is what you have to be sure when you are constructing this particular mesh. Okay, so this is about how you can fix this. Along with that we have a grading, and we require the non-uniform mesh. So wherever there is a solid wall, that means in our case solid wall is at a location of this circular cylinder. Okay, so we must have a refined mesh towards this part. Okay, so and if you look at 2 to 3, okay, so 2 to 3 we constructed as a 2 to 3 is the x direction. Okay, and x mean 1. Here you look at refinement I gave as a opposite way. Okay, so that means if you look at check this 2 to 3 edge, so 2 to 3 edge here. So if I want refinement towards 3 size, okay, if I require refinement in towards the 2, then I require the value expansion ratio more than 1, but in this case we require refinement towards the 0.3. so in that regard, if you check the refinement xm1 refinement 1, that also I set here is something like 0.2, all in the below the 1 form. So that what it mean that when we specify, all the mesh is going to cluster towards the 0.3. okay, that it mean. And 2 3 is the x-axis. How we can say 2 3 is x-axis? From whatever we specify first, 2 3 is x-axis and 3 0 is the y-axis. Okay, so 2 3 is x-axis and 3 0 is the y-axis. That is how you can give the number of element in that regard. Okay, so that is what we did, and in the y direction we don't require any type of the non-uniformity. That's why it is a uniform. So try to explore step by step all this line and try to understand what exactly happened while we develop this particular mesh. Okay, now few more entry you can see. This is the edge. Okay, so we required the arc. Where we required the arc? We required the arc to construct this particular circular object. Okay, so if we want to construct this circular object, we require arc between point 0 to 3, and its center point is supposed to be, if it is the, let's say 0.5 is the radius. Because why I say 0.5? Because the centroid of this is at the 0 0 0. Okay, so 0.5 in x direction positive, 0.5 minus 0.5 in the y negative y direction, same way positive 0.5 in y direction, negative 0.5 in y direction. That is goes in the centroid of this. So if we want to construct the arc, what we required? We require the location of 2 points. So location of 2 point is 0 and 3. Please understand, between we are constructing the arc between 0 and 3, and we require the midpoint of this particular location. So for that, in that regard, midpoint is 0.5 0, and this z we kept as a plus and minus 0.5. Okay, so that's why in the x diagram, if you see y equal to exactly, let me put it something like this way. Okay, so when you see this is a centroid, so this point is positive 0.5 and y equal to 0, and that is in the back side of the geometry, so it is minus 0.5, and front side is the z equal to plus 0.5. so like that way we constructed all the arcs. Okay, so this arcs, these 4 arcs is giving you the idea about the this circle, okay, top circle. This another 4 arc give you the bottom circle, and this 4 arc give you the idea about this 2 bigger circle that will allow us to create very nice mesh with the help of these arcs. Okay, so that is few entry you can check from here. Okay, that is additional as compared to others. Now we require the patch, so we require the inlet outlet. So let me on all the blocks. So what we required these all 3 patches. With 3 patches, 1, 2 and 3, it's supposed to be the inlet. Similar line, these 3 patches 1, 2 and 3 is supposed to be the outlet. Then this 1, 2, 3, okay, that's supposed to be the symmetric plane 1 and symmetry plane 2, symmetry 1 and symmetry 2, top and bottom. Okay, so there you have a 3, 3 face, and this front and back empty, where you exactly have how many face? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 faces come at a front and back. Okay, back front and the empty front and empty back. So like that way you are able to construct entire of this geometry. Along with that, there is a blank entry available, merge patch pair, that is not required here. Later on we explore this option. So with the help of this block mesh, we are able to construct very nice mesh for a flow over a circular cylinder. So let's construct and try to check how the mesh is look like. So block mesh, so how many patch we have? We have inlet, outlet, cylinder. Okay, I forgot to mention, whatever the patch is falling inside the cylinder, it goes toward the cylinder patch. Okay, then symmetry 1, symmetry 2, front and back, that going as empty. And if you check here, we have a different blocks. So total we blocks starting from 0, okay, and 0 till 11, so total we have 12 blocks in it. Okay, and let's see the check mesh. So if you see the check mesh is quality is fine. Here also you able to see number of patches. Okay, and then here is the total number of cells that we have. So it is something like 12k approximately. Okay, and internal phase and external phase. So this type of mesh is called the multi-block type of the mesh. Okay, let's check again the mesh, how it look like. Apply. Okay, and H. So if you see the mesh is something like this way. Okay, so we have a fine mesh near the wall, okay, where we require the better capturing of the boundary layer, and if we able to capture very nicely, our CDCL value will be matching with the open literature. Okay, so that is the idea. So this is how you can construct the mesh. Now let's quickly try to run the case. That is the idea. Okay, so let's now, for running the case, we going to utilize the OpenFOAM. Before we start simulation, we make sure that we are setting all the property correctly. Okay, so let's we want to run for r equal to let me check, 250. Yeah, r equal to 250 we want to run, and our cylinder diameter is 1 meter. Okay, so in that regard, if you see, then our nu, if we specify at the inlet 1 meter per second, then nu supposed to be something like 4 10 to the power minus 3. Let's check what is the inlet velocity we specified. Okay, so at the inlet we have in the inlet plane we have a fixed value. In the x component to specify 1 meter per second. Okay, outlet, we have an inlet outlet. What it allow the reverse flow phenomena by checking the phi value. Okay, so it's check the flux, and if the flow is going out, then it will explicitly put as a pressure outlet. If it is coming inside, then it will mimic the Neumann for the pressure and velocity it goes as the incoming velocity. So it is a very good condition as compared to this, because if we specify the zero gradient, then we able to we not able to achieve the very good von Karman street, that is the vertex shading that we going to get behind the circular cylinder. So as compared to this is a better condition, but best condition is the Orlowski condition. Okay, so later on we explore how we can code that part. Okay, and cylinder is the wall condition, and front, top and bottom plane is the symmetric plane. So we specify the symmetric plane, and front and back is empty because we want to simulate it as a 2D flow. In the similar line, if you look at the pressure, so where we specify the velocity, we specify velocity at the inlet plane, so we are specifying it as a zero gradient. Okay, at the outlet we specify fixed value for pressure. Okay, and if on the cylinder, again the zero gradient, and symmetry plane no need to specify, front and back empty, no need to specify. Okay, so like that way we set the boundary conditions and the transport property. Let's explore few entries in the control dict file. If we have few more entry, so our simulation going to start with the OpenFOAM. Okay, few more entries that we're going to discuss in the next lecture. Okay, about all these entries, but right now what I want to say, there is a few more functions I activated, like inflow mass flow rate, okay, as well as outflow mass flow rate, to compare either our mass flow is going correctly or not. Then field averaged, if it is unsteady flow, then after some time we supposed to start the field averaged. Okay, so that purpose this portion is available. What it going to give you, it give you the time averaged flow field, the mean is on, statistic is also on. Okay, and then we have to calculate certain force on the circular cylinder, because we are interested how the viscous and pressure force is acting on the circular cylinder, because we are interested in the external aerodynamic type of the simulation. So for that this is here, and coefficient. So with the help of this we are able to calculate the lift and drag coefficient. For lift our direction is in the y direction, and for the drag in the x directions. Okay, incoming velocity is 1 meter per second. Okay, and the reference density we are considering is a 1. With the help of this we able to capture the CD and CL value over where circular cylinder is the patch name. Okay, then mix min maximum of the domain, and we require the pressure maximum minimum and the velocity maximum minimum. So these few entry you can see. Later on we going to explore all these entries, but right now you consider as a few more output you're going to see when we run the simulations. Okay, along with this let's explore what we have in the scheme files. Okay, so now we are working unsteady flow, so either we go with Eulerian type of implicit scheme or backward type of implicit scheme, or the Crank-Nicolson. So 0.5 is the blended scheme. That means it is if it is 0 it's purely Euler scheme, and if it is 1 then purely Crank-Nicolson scheme. Right now it is intermediate. Okay, for gradient we are using some other type of the scheme, that is lit square type of the scheme. Previously we are using some Gaussian linear center difference scheme. Okay, divergence we are using linear upwinding. Okay, default, that means this default is exactly this one. Okay, when they want to calculate the gradients. Okay, that means to calculate on the phase gradient. Then we have Laplacian scheme. Okay, Gaussian limited scheme we are using. Okay, interpolation scheme is linear, and sun gradient, previously it is corrected, now limited 1. Okay, so this is all entry. We have few more, and then solution wise if you see, we are using GMG solver for pressure final. We have a same solver what we going to use for pressure, but relative tolerance we go towards 0. It is the same, so we are not changing anything, same solver. But if you think at the what it mean, why you have a pressure and pressure final, because of this n corrector. Okay, so when we are working with the first corrector you work with this, but at the final correction you can even change this tolerance. Sometimes what people do for faster result, they reduce the tolerance to 10 to the power 4 for intermediate corrector, but for final corrector they go with the 10 to the power 6 with a very stringent parameter. Okay, so that is how you can control and speed up your simulation. For U we are using preconditional BiCG step method. It is a much robust linear inverter matrix method. Okay, so and here we need not to specify the pre-ref reference value. Why? Because we are explicitly specifying the pressure at the outlet. Okay, so pressure equal to 0, so we need not to specify, so we commented that part. Along with that, our mesh is not exactly the Cartesian mesh. Some places we have a slightly skewed element, so for that we apply the non-orthogonal correction as well, and this is number of n correctors. So right now we are working with very small Reynolds number. Later on, when you increasing the Reynolds number, maybe this setting you have to refine. Okay, maybe that means n corrector you may increase something like 3 to 4, or this non-orthogonal correction you can increase something like 5 to 6. Okay, and if your simulation is stabilizing. Okay, so that is how you different setting we have. One thing I forgot to mention is this delta t. Okay, so when you increase the RE, please also change this delta t. Okay, because that is otherwise current number may shoot up and we go towards the divergence of the simulations. Okay, so let's now run this particular case, so it gives us the idea what is going on. Okay, so let's start the simulations. Okay, I already started, and this is the output, that file. Okay, let's see. So here we are seeing that at the beginning it's going to converge, and then when the vertex shading is start, it's going to start oscillating. But if you exactly want to see the oscillation and everything, then here I also gave you certain script files. Okay, so that script file you can use with the help of the GNU plot. So I will show you how you can use that. GNU plot, then script, then what is the name, plot. Okay, plot. Let's say we want to look at how the CD is going on while the simulation is running on. Okay, so our simulation is progressing till this CD is going down and down. Later on, what happen when the vertex shading is start, the CD is start oscillating. Okay, sometime what happens, CL value give very quick oscillation as compared to CD. Yeah, exactly. So look, now CD is still going down, but CL, even though it is very low value, but it start oscillating. Okay, so when it's giving you the bigger size of oscillation, that means the vertex shading is about to start. Okay, so let's look at in the paraform how the simulation is progressing. Okay, so this is the U. Okay, and let's start simulation. So we till reach 42 seconds and it's yet to start the shading. Okay, so later on when this separated bubble is becoming very large, it starts shading from top to bottom. Here is the refresh time. When you do refresh time, okay, it will allow you to further look at the data whatever till now simulated. Okay, look, now it's almost going to start the shading after a few more iterations. Look, we are almost approaching the place from where the shading going to start. Okay, so let me run from the scratch. Still it is a very coarse mesh. Okay, so it is not the appropriate mesh to simulate this class of the flows, but we are just mimicking certain tutorials. Okay, so that's why I am working with very coarse mesh. Now the vertex shading is started. Okay, so now vertex shading is started, so let's explore how the CL is look like. Look, CL is getting bigger and bigger. Okay, positive to negative. Similar line, you can see the CD value as well. Okay, so CD is now approaching. Okay, and slowly in the CD also you will see the continuous up and down with respect to one particular mean value. Okay, so that is what we can see, but till the simulation is not approaches dynamic nature. Why we can say? Because till the CD and CL value is changing. How we can say that simulation become dynamic nature? When you will get a repeated this jump. Look, from here to here there is a big jump. Now it's slowly going to change. Okay, so I think within another 50 to 20 second run, we going to get a very nice repeated vertex shading from top to bottom part of the circular cylinder. Then we say, okay, now our simulation approach the steady state. It is not called steady state, but it is called dynamically state nature. Why it's called dynamic steady state or dynamic nature? Because now we have a repeated vertex that will in the same size and with the same frequency going to depart from the surface of the circular cylinder. Okay, so look, now it's almost become uniform. Okay, let's explore from the CD as well what happened. Yeah, CD also almost mature. Okay, so if this is the case, now you can stop the simulation. If you are only interested in the calculation of, let's say, what is the Stroll number, then we have to open this in different config, maybe tech plot or so, and this data, and we can figure it out what is the time lag in between this repeated pick. Okay, so if we know the time, reverse the time, it gives you the frequency, and from that you calculate the Stroll number and try to match with the open literature. Let me show you how the para view is progressing. Okay, so if you see the para view, let me zoom in the area where we are interested. Let me cut the slice. Okay, here is slice and this is the velocity. Let me go straight away at the end, and what I did, I went here. Okay, so I reached the last slide and then rescale the data. So based on that, it will scale very nicely. Now come back at the first slice from here and then start simulation, start animation ultimately. Okay, so here you can see after some time, okay, it start oscillating. Okay, so this is what we supposed to get from the top and bottom. The boundary layer is depart and become the free shear layer, and that free shear layer subsequently roll down in terms of the very nice vertex. Okay, so positive to negative going to rotate. Okay, let's create streamline, how it look like. Okay, so high source, x-axis. Okay, so this is how the streamline is look like. If we zoom in this area, you can see very quickly. Okay, so previously this vertex is becoming bigger. Okay, and then it's slowly going to depart. Okay, and when it start departing, okay, slowly we can see later on when the vertex shading is started. Okay, how exactly it's departing from the top and bottom side alternatively. Now look, it's almost becoming asymmetric. Okay, slowly we will get the vertex shading. Now vertex shading is about to start. Okay, so look, now we get alternative shading of the vertex from top and bottom part. Okay, so this is how one can see the simulation result in the this flow over the circular cylinder. Okay, so I suggest try to utilize this tool effectively, try to construct the let's say animation out of it. Okay, so okay, let me stop here. So let's check where our CDCL value reached. So look, it's almost pretty good, but till simulation is going on. Why? Because maybe we kept a very high value in the control dict file. Our end time we set as a 350, so until unless you reach the 350, our simulation will be continue. But if you want, then you can stop like this way, stop, change to stop now. Okay, and save it. Okay, so our simulation is now stopped. If you see here, you can see it's come out. Just check top command, nothing is running. Okay, look at the our directory, so many directory is stored. Why? Because we told that after every one times, after every 1 second, it's supposed to write a data. Okay, so that's why you can see writing interval is run time. Okay, so every now and then it's try to store a data, and we didn't kept the purge right. Okay, so if you think that that many data is too big to handle, okay, then I suggest then you can change this purge right to something like 10, 20 or 30. Okay, then but if you are interested to create starting till end entire animation, then all the data is required. Okay, if you say purge right equal to 10, then at that time you have only 10 backup files. So let's say it's, if we start from something like 20, 21, 20, when it try to dump the 31, at that time it try to delete the 21 file. Okay, so like that way at a time you only have a total 10 backup file. And so when you are working with something like transient flow and you are interested only with the final result, then try to use this purge right. It will save lots of our hard disk memory. Okay, so that is what I can say. So what we look at in this tutorial, very quickly we look at the flow over a circular cylinder part. Okay, and we try to run for r equal to 250. Okay, so that is what we did. Now let me open our parent directory tutorial. Okay, so look, right now I gave you only one mesh file. Okay, so this is the exercise that you have to execute. Okay, now change the mesh file. Okay, so when you are changing the mesh file, what different parameter you supposed to change? You supposed to change certain more parameter from this file. So I will show you from block file. So when you want to refine the mesh in the particular zone, okay, so C1 zone, let me give you the idea about this zone as well. So let me open the block. Okay, so this is the C1 zone. Okay, so please understand, this is the place if you want to modify the mesh size. Okay, so this is different places you can give the mesh size. Let me check again. C2 zone is belong to the this portion. Okay, C2 zone is belong to that portion. That means C2 zone is belong to this one. Okay, so if you want to refine the mesh in near to the circular cylinder, you have to work with the C2 and Y2. Okay, C2 and Y2, and C1 and C4. Okay, C1, that means XC1, I am talking about XC1, XC2, YC1, YC2. If you want to refine the mesh in this area where we have a circular cylinder, okay, then you have to change which parameter? Then you have to change this parameter. That means you have to change the mesh size at this level. Okay, this and this. Okay, if you refine these two parameter, it allows you to refine the mesh near the circular cylinder. Okay, so try to get a feeling how you able to change the mesh size by understanding this entire block mesh file. Okay, it is a big task, I know, but please spend good amount of time to understand this entire block mesh file. Okay, if you're not able to understand, then I will make you understand during our live discussion. Okay, but I think please spend some time. Okay, so that give you the added advantage when we try to discuss the same blocking file if you require. So what I want from your side is following thing. Okay, please try to create few more mesh files. Okay, and try to run the case for 10. So 10 and 25 maybe you will not going to get a vertex shading, but after 50 may you get a vertex shading, then 100 and 250. Okay, validation I wrote. Why I am asking you to search a paper that will give you the Stroll number for flow over a circular cylinder for r equal to 100 and 200. Here I gave maybe one paper with respect to that. So couple of paper I gave you. Okay, so try to look at out of this some of the paper explaining what's supposed to be the Stroll number. Okay, try to find out the Stroll number, figure it out. Are you getting the correct Stroll number? If not, then you have to go towards the mesh refinement. So this study you can consider it as a something like a grid independency type of the studies. Okay, so normally this is very important step when you want to go towards publication type of the project, okay, or if you are going to industrial project, then it not matter a lot, okay, because in industry everything is set, all parameter is set. But when we want to look at academic project, then this grid independent study is very, very important. So with the help of that, I suggest try to first look at the grid independency. With the grid independency, I suggest try to check with higher RE 250 or 200, so that you get a very good Stroll number mapping, okay. And so try to do certain exercise with that, and then go towards the very high RE. When you go toward very high RE, I suggest go with a very low delta t. That means the time step supposed to be reduced, and make sure your cohort number don't shoot out more than something like 1. I suggest go something like 0.5. It is a very good value, okay, even though simulation not going to diverge up to let's say Stroll number equal to 1, but I suggest stick to the Stroll number, sorry, not Stroll number, coherent number, something like 0.5 or so, okay. So that is what I want from your side. So please spend decent amount of time and go through this particular tutorial. It is a very, very good tutorial to explore the unsteady nature with the help of the ICOFOAM, okay. So I hope you understand this. Okay, so let me stop here.